Hello there and welcome. Tonight's peaceful journey explores the grandest question of all. What is this universe we call home? It stretches beyond every horizon, hums with invisible forces, and somehow contains everything from morning coffee to distant galaxies. But before we drift through this cosmic tapestry, I'd love to know where in this vast universe you're listening from tonight, and what small corner of space you occupy right now. Fitting, isn't it? A conversation about everything, and here we are, scattered across the cosmos, each arriving at this moment from our own unique point in space and time. So settle in, slow your thoughts, and let's begin this gentle exploration, because somewhere between atoms and galaxies, between quantum whispers and cosmic roars, lies the story of absolutely everything. The universe has a peculiar way of being both utterly familiar and completely alien. You wake up each morning in the same bedroom, perhaps sip the same coffee, follow the same routines, and yet you're hurtling through space at incredible speeds on a planet that's spinning around a star that's racing through a galaxy that's rushing toward some distant gravitational pull. Every breath you take contains atoms that have journeyed across the cosmos, been part of ancient stars, danced in the hearts of distant suns, and somehow found their way to your lungs on this particular evening. The word universe comes from the Latin universum, meaning turned into one. And there's something profoundly beautiful about that etymology. Everything we've ever known, everything we could ever know, every thought that's ever been thought, and every star that's ever shone, all turned into one magnificent interconnected whole. When you look up at the night sky on a clear evening, you're not just seeing distant lights. You're peering into your own cosmic heritage. The iron in your blood was forged in the nuclear furnace of a dying star. The calcium in your bones was scattered across space by a stellar explosion that happened billions of years before Earth even existed. You're not separate from the universe. You are the universe, temporarily arranged in a pattern complex enough to wonder about itself. But what exactly are we wondering about? When we say universe, we typically mean everything that exists, all matter, all energy, all space, all time, all the forces that govern how things interact, and all the laws that describe how reality operates. It's the stage and the play, the canvas and the painting, the instrument and the music all rolled into one. Yet the more we study this cosmic everything, the stranger it becomes. Most of it is invisible to us. Most of it operates according to rules that seem to defy common sense. Most of it exists in forms we can barely comprehend, let alone observe directly. Scientists estimate that ordinary matter, the stuff we can see and touch and understand intuitively, makes up only about 5% of the universe. The rest is divided between dark matter, which we can detect through its gravitational effects but can't see, and dark energy, which appears to be accelerating the expansion of space itself, but remains completely mysterious. So when we ask, what is the universe, really? We're essentially asking about something that's 95% unknown. It's like trying to understand a book when you can only read one page out of every 20, and even that page is written in a language you're still learning to decipher. This mystery isn't a failure of science. It's an invitation to wonder. Every generation of humans has looked up at the night sky and asked the same fundamental questions. Where did all this come from? How big is it? Are we alone? What does it all mean? And while our instruments have grown more sophisticated and our theories more elaborate, the essential sense of awe remains unchanged. A child seeing the Milky Way for the first time experiences the same cosmic vertigo that struck ancient philosophers and modern astronomers alike. There's something irreducibly humbling about contemplating infinity, something that makes our daily worries seem both infinitely small and paradoxically more precious. The universe also has this delightful habit of being counterintuitive. It began in a state that was simultaneously everything and nothing, exploded outward in a way that created space rather than expanding into it, and continues to evolve according to rules that seem more like poetry than physics. Particles exist in multiple states simultaneously until observed. Space and time are woven together into a fabric that can bend and stretch. Information cannot be destroyed, even when it falls into a black hole. The universe operates like a cosmic puzzle, where every answer reveals 3 new questions, each more intriguing than the last. And yet, for all its strangeness, the universe feels like home. After all, we didn't arrive here as visitors from somewhere else. We emerged from the universe itself, the way a wave emerges from an ocean, or a song emerges from silence. Our capacity for wonder, our ability to ask these questions, our tendency to find beauty in cosmic phenomena we'll never directly experience. All of this suggests a deep harmony between consciousness and cosmos. We are the universe's way of knowing itself. Temporary arrangements of stardust complex enough to contemplate the very stardust from which we're made. So as we embark on this gentle journey through everything that is, remember that you're not just learning about the universe. You are the universe learning about itself. Every moment of understanding is a moment when the cosmos becomes more self-aware. Every question you ask is the universe asking questions about its own nature, and every sense of wonder you feel is the universe marveling at its own magnificent complexity. Tonight, let's explore this cosmic home of ours together, drifting through space and time and mystery with the patience of starlight and the curiosity of conscious beings who somehow learned to love the very darkness from which they emerged. The universe has a funny way of making us feel simultaneously important and impossibly small. You're sitting there, a collection of atoms that somehow learned to think, on a planet spinning through space at 67,000 miles per hour, orbiting a star that's one of hundreds of billions in our galaxy alone. And our galaxy? Just one of trillions scattered across observable space. Yet here you are, conscious, aware, able to ponder it all. The universe isn't just big. It's so magnificently enormous that our brains simply can't grasp it fully, so we measure it in numbers and settle into wonder. Let's start with something manageable. You're roughly 6 feet tall, give or take, which seems like a reasonable size for a conscious being, but zoom out just a little, and you become invisible on your city block. Zoom out further, and your entire city disappears into the curve of Earth. From the moon, our whole planet looks like a pale blue dot suspended in cosmic darkness. From the edge of our solar system, Earth vanishes entirely, lost in the glare of our sun. And our sun? It's a perfectly ordinary, medium-sized star among the roughly 400 billion stars in our Milky Way galaxy. Now, if you could somehow step back and view our entire galaxy, it would appear as a magnificent spiral of light, about 100,000 light-years across. That means light, traveling at 186,000 miles per second, takes 100,000 years to cross from one edge to the other. Put another way, if you were the size of a bacterium, the Milky Way would be roughly the size of Earth. But even this vast spiral of stars is just one galaxy among countless others. The nearest major galaxy to ours, Andromeda, is about 2.5 million light-years away. If the Milky Way were the size of a dinner plate, Andromeda would be another dinner plate about 25 feet away. And this is just our local cosmic neighborhood. Galaxies cluster together in groups, and these groups cluster into larger structures called superclusters. And these superclusters arrange themselves into vast filaments and walls separated by enormous voids. The observable universe, the part we can actually see, extends about 46.5 billion light-years in every direction. Why not 13.8 billion light-years, if that's the age of the universe? Because space itself has been expanding while light has been traveling toward us, stretching distances in ways that would make even Einstein pause to recalculate. But here's where it gets truly mind-bending. The observable universe might be just a tiny fraction of the actual universe. Imagine standing in a vast fog where you can only see 100 feet in any direction. That circle of visibility doesn't represent the edges of the world, it just represents the limits of your perception. Similarly, the edge of the observable universe isn't a wall or a boundary, it's simply the limit of how far light has had time to travel since the Big Bang. Beyond that horizon lies more space, more galaxies, more stars, possibly infinite in extent. Some cosmologists suggest the universe might be truly infinite, meaning that somewhere out there, purely by chance, every possible arrangement of atoms has occurred. That would mean there are infinite copies of you, reading infinite variations of this very script, on infinite variations of Earth, scattered throughout infinite space. It's a concept that makes infinity feel less like a mathematical abstraction and more like a cosmic truth that our finite minds can barely whisper about in the dark. Yet for all this incomprehensible vastness, we're discovering that the universe operates according to surprisingly elegant rules. The same gravity that makes an apple fall from a tree also governs the orbit of planets around stars and the dance of galaxies around each other. The same electromagnetic forces that power your heartbeat also fuel the nuclear reactions that make stars shine. The same quantum mechanics that governs the behavior of electrons in your brain also determines how atoms formed in the early universe, and how black holes might eventually evaporate. This unity across scales is one of the most beautiful aspects of cosmic study. When you learn that the patterns of neural networks in your brain resemble the large-scale structure of the universe, or that the mathematics describing market fluctuations also describes the distribution of galaxies, you start to sense an underlying harmony to existence. It's as if the universe composed itself according to a few fundamental themes, and then improvised infinite variations on those themes across every possible scale and context. The numbers themselves become a kind of poetry when you contemplate them long enough. There are roughly 7 octillion atoms in your body, which is a 7 followed by 27 zeros. There are approximately 100 billion neurons in your brain, roughly the same as the number of stars in our galaxy. The observable universe contains about 2 trillion galaxies, each containing billions or trillions of stars, most of which likely host planetary systems, some of which might harbor life. These aren't just statistics, they're invitations to wonder about connection, complexity, and the sheer improbability of conscious beings emerging from cosmic chaos. What makes the scale even more remarkable is the precision required for any of this to exist at all. If the universe expanded slightly faster after the Big Bang, matter would have spread too thin for stars and galaxies to form. If it expanded slightly slower, everything would have collapsed back into a cosmic crunch before complexity could emerge. If the electromagnetic force were marginally stronger, stellar nucleosynthesis couldn't produce carbon and other elements essential for chemistry and life. If gravity were infinitesimally different, planets couldn't maintain stable orbits around stars. The universe appears to exist in a narrow band of possibilities where structure, complexity, chemistry, biology, and consciousness can emerge. Some call this the anthropic principle, the observation that the universe seems fine-tuned for the existence of observers like us. Whether this represents cosmic design, infinite parallel universes with different parameters, or simply the selection bias of conscious beings who can only observe universes capable of producing them, remains one of the deepest mysteries in cosmology. But perhaps the most astonishing aspect of cosmic scale is that we can comprehend any of it at all. Here you are, a temporary arrangement of atoms roughly 5.5 feet tall, somehow capable of understanding objects billions of light years away and events that happened billions of years ago. Your brain, which weighs about 3 pounds and could fit in your cupped hands, contains more neural connections than there are stars in our galaxy. You are both infinitesimally small in cosmic terms and infinitely complex in structural terms, a bridge between the quantum realm and the cosmic realm, matter organized in such an intricate way that it can contemplate the very matter from which it's made. So yes, the universe is unimaginably vast, but it's also intimately personal. Every atom in your body has a cosmic story stretching back to the beginning of time. You are not separate from the universe, contemplating it from the outside. You are the universe contemplating itself from the inside. Your capacity for wonder at cosmic scales is itself one of the most wonderful things about the cosmos. In sensing your own smallness, you participate in something infinitely large. In feeling humbled by infinity, you touch something infinitely profound. The universe may be too big to fully comprehend, but it's exactly the right size for wonder, exactly the right scale for mystery, and exactly the right complexity to give rise to conscious beings who can appreciate the magnificent impossibility of their own existence under an infinite canopy of stars. Once upon a time, about 13.8 billion years ago, there was nothing. No space, no time, no matter, no energy, just nothing. Then, in an instant smaller than a heartbeat, everything began. Scientists call it the Big Bang, though it wasn't really an explosion but rather the sudden expansion of space itself. Imagine a balloon inflating, but the balloon is reality, and there's nothing outside it. In the first fraction of a second, the universe grew from smaller than an atom to larger than a grapefruit, creating space, time, and the seeds of everything that would ever exist, including you, listening softly in the dark. But let's pause for a moment on that word nothing, because it's harder to imagine than you might think. When we say nothing existed before the Big Bang, we don't mean there was an empty void waiting to be filled, like a dark room waiting for someone to turn on the lights. There was no room. There was no darkness. There wasn't even a before in any meaningful sense, because time itself hadn't been invented yet. It's like asking what's north of the North Pole, or what happened before the first moment of your favorite song. The question seems to make sense, until you realize it's asking about something that, by definition, cannot exist. This absence of everything is so profound that our language struggles to describe it. Even the word nothing implies something, some sort of empty container where nothing resides. But the pre-Big Bang state wasn't even that. It was the absence of absence, the lack of lack, a condition so thoroughly without properties that calling it a condition already says too much. And yet, somehow, from this ultimate nothing came the ultimate everything. The universe didn't expand into empty space. It created space as it expanded. Time didn't start ticking in some cosmic clockwork. Time came into being along with everything else. The first moment of this cosmic story unfolds in periods so brief they make a blink of an eye seem glacially slow. In the first 1043 seconds, called the Planck epoch, the universe was so hot and dense that our current physics breaks down entirely. Space and time themselves were probably quantum phenomena, flickering in and out of existence like foam on an infinite ocean. The four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single, incomprehensible superforce. The universe was smaller than a proton, but contained all the energy that would eventually become every star, planet, and galaxy. Then came cosmic inflation, one of the most remarkable concepts in modern cosmology. Between 1036 and 1032 seconds after the beginning, space expanded exponentially, doubling in size more than 60 times in less time than it takes light to cross a proton. This wasn't matter moving through space. This was space itself, stretching so rapidly that regions of the early universe that started out in contact were suddenly separated by distances vastly larger than the observable universe today. It's like blowing up a balloon so fast that two ants walking on its surface suddenly find themselves on opposite sides of something larger than a city, than a continent, than a planet, all in the time it takes to snap your fingers. This inflationary period explains several puzzling features of our universe. It explains why space appears flat on the largest scales, why the cosmic microwave background radiation has almost exactly the same temperature in all directions, and why we don't see certain exotic particles that theories predict should have been created in the early universe. Inflation stretched these irregularities and particles beyond our observable horizon, leaving us in a small, smooth patch of a much larger, more varied cosmic landscape. As inflation ended, the universe entered a period of reheating, where the energy driving expansion was converted into matter and radiation. The temperature was trillions of degrees, hot enough that even protons and neutrons couldn't hold together. Instead, space was filled with a plasma of quarks, gluons, and other fundamental particles, all bouncing around in a cosmic soup so energetic that particle physics experiments on Earth can only recreate tiny glimpses of these conditions. By the time the universe was a few microseconds old, it had cooled enough for quarks to combine into protons and neutrons, the building blocks of atomic nuclei. This was the first moment when anything resembling the matter we know today could exist stably. Yet even now, the universe was still far too hot for atoms to form. Electrons existed, but they had too much energy to be captured by nuclei. Instead, they zipped around freely, making space opaque to light like a cosmic fog. The universe continued expanding and cooling, and when it was about 3 minutes old, something remarkable happened. The first atomic nuclei formed through a process called Big Bang nucleosynthesis. Protons and neutrons began sticking together to form deuterium, helium, and trace amounts of lithium. For about 20 minutes, the entire universe was essentially a gigantic nuclear reactor, fusing light elements at temperatures and densities that modern stars can only achieve in their cores. When the temperature dropped below the threshold for nuclear fusion, this cosmic reactor shut down, leaving the universe with roughly 75% hydrogen and 25% helium by mass, proportions we still observe in the oldest stars today. But the universe remained opaque for much longer. For the next 380 years, space was filled with hot plasma, electrons and nuclei bouncing around freely, scattering photons in every direction. During this period, matter slowly began to clump together under the influence of gravity, but the process was gradual and hidden from view. The universe was like a vast, glowing fog, uniformly bright but impossible to see through. No stars existed yet, no galaxies, no complex structures of any kind, just the slow gravitational dance of invisible matter in a sea of scattered light. This early period reveals something profound about the relationship between simplicity and complexity. The universe began in the simplest possible state, essentially uniform and featureless. Yet built into this simplicity were tiny quantum fluctuations, microscopic variations in density that inflation stretched to cosmic scales. These fluctuations were incredibly small, less than 1 part in 100, zero. But they provided the seeds around which all future structure would grow. Gravity, that most gentle of forces, slowly amplified these tiny variations. Regions that were slightly denser than average attracted more matter, becoming slightly denser still, which attracted even more matter, in a process that would eventually create the cosmic web of galaxies and galaxy clusters we see today. But this process takes time, enormous amounts of time by human standards. And in those first few 100,000 years, the universe was still too young and too hot for dramatic structures to emerge. The beauty of this origin story lies not just in its cosmic scope, but in its elegant simplicity. From the incomprehensible complexity of quantum gravity in the first instant emerged the 4 fundamental forces that govern all interactions. From the cosmic inflation that made space uniform emerged the tiny fluctuations that would seed all future diversity. From the nuclear furnace of the first few minutes emerged the light elements that would eventually form stars, planets, and the chemistry of life. Each stage of the early universe set the conditions for the next, like a cosmic symphony, where each movement establishes the themes that will be developed and elaborated in movements yet to come. The universe keeps old photographs of itself, and we can still see them tonight. About 380, 0 years after the Big Bang, space cooled enough for the first atoms to form, and light could finally travel freely. That ancient light is still out there, stretched and cooled by billions of years of cosmic expansion, now appearing as faint microwave radiation filling every corner of space. It's like the universe's baby picture, showing tiny ripples that would eventually grow into galaxies and stars. Turn on an old television to static, and about 1% of those dancing dots are echoes of creation itself, gently crackling. This cosmic microwave background, as scientists call it, represents one of the most profound discoveries in the history of astronomy. It's the afterglow of creation, the fading echo of the moment when the universe first became transparent. For nearly 380 years after the Big Bang, space had been opaque, filled with hot plasma where electrons and protons danced separately, scattering photons like a cosmic fog. But as the universe expanded and cooled, something remarkable happened. The temperature dropped just enough for electrons to be captured by protons, forming the first neutral hydrogen atoms in a process called recombination. Suddenly, for the first time in cosmic history, light could travel freely through space. The universe went from being like the inside of a star, where photons constantly scatter off charged particles, to being like the space between stars, where light can journey for billions of years without obstruction. This moment, sometimes called the surface of last scattering, released a flash of light that filled the entire universe. But this wasn't light as we normally think of it. Due to the extreme temperature, this primordial radiation was initially in the form of visible and infrared light, glowing with the heat of creation itself. As the universe continued to expand over the following 13.8 billion years, something beautiful and subtle happened to this ancient light. The expansion of space itself stretched the wavelengths of these photons, gradually shifting them from visible light through infrared and finally into the microwave portion of the electromagnetic spectrum. This is why we call it the cosmic microwave background. It's not that the early universe was naturally producing microwaves. Rather, the microwaves we detect today are the stretched and cooled remnants of what was once brilliant, hot light filling all of space. The discovery of this radiation is one of science's most elegant detective stories. In 1948, physicists Ralph Alpher and Robert Herman predicted that if the Big Bang theory was correct, there should still be detectable radiation left over from the early universe. They calculated that this radiation should have a temperature of about 5 degrees above absolute zero, corresponding to microwave frequencies. For nearly 2 decades, this remained a theoretical prediction, a whisper from the equations suggesting that the cosmos had left us a message written in the language of light. Then, in 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate sources of interference from their sensitive microwave antenna. No matter what they did, they couldn't get rid of a persistent background noise that seemed to come from every direction in the sky. After ruling out terrestrial sources, including pigeons nesting in their equipment, they realized they had stumbled upon something extraordinary: the cosmic microwave background itself, with a temperature of 2.7 degrees above absolute zero, remarkably close to the theoretical prediction. This discovery provided stunning confirmation of the Big Bang model and opened an entirely new window into the early universe. But the cosmic microwave background radiation isn't just important because it proves the universe had a hot, dense beginning. It's important because it carries detailed information about conditions in the early cosmos, like a cosmic time capsule containing blueprints for everything that would come later. When we map the cosmic microwave background across the sky, we see something that appears almost perfectly uniform at first glance. The temperature varies by only about 0.00001 degrees from place to place, making it one of the most uniform things in nature. But hidden within this near-perfect uniformity are tiny fluctuations, microscopic variations in temperature that correspond to tiny differences in density in the early universe. These fluctuations are the cosmic seeds from which all large-scale structure would eventually grow. Think of it this way: if the early universe had been perfectly uniform, with exactly the same density everywhere, gravity would have had nothing to work with. There would be no preferred locations for matter to begin clumping together, no starting points for the formation of stars and galaxies. The universe would have remained forever smooth and featureless, a cosmic soup that never learned to make interesting patterns. But the quantum nature of the very early universe ensured that tiny fluctuations existed, variations so small they seem almost insignificant, yet profound enough to make all future complexity possible. These temperature fluctuations in the cosmic microwave background correspond directly to density fluctuations in the matter distribution of the early universe. Slightly warmer regions correspond to areas that were slightly less dense, while slightly cooler regions correspond to areas that were slightly more dense. Over hundreds of millions of years, gravity would amplify these tiny differences. The denser regions would attract more matter, becoming denser still, eventually forming the first stars and galaxies. The less dense regions would empty out, becoming the cosmic voids we observe today. Modern satellite missions have mapped these fluctuations with extraordinary precision. The Cosmic Background Explorer first detected them in the 1990s, earning a Nobel Prize for its team. The Wilkinson Microwave Anisotropy Probe and the Planck satellite have since mapped them in exquisite detail, creating baby pictures of the universe that reveal not just what the early cosmos looked like, but also fundamental parameters like the age of the universe, its geometry, and the relative amounts of ordinary matter, and dark energy. The patterns in these fluctuations tell us remarkable things about the physics of the early universe. The size and shape of the temperature variations depend on the speed of sound in the early plasma, which in turn depends on the balance between radiation pressure, trying to smooth things out, and gravity trying to clump them together. By analyzing these patterns, cosmologists can determine how much ordinary matter exists, how much dark matter there is, whether space is flat or curved, and even details about cosmic inflation in the first fraction of a second after the Big Bang. One of the most striking features of the cosmic microwave background is what it tells us about the geometry of space itself. If the universe were curved like the surface of a sphere, distant objects would appear larger than expected, and the fluctuation patterns would be stretched. If it were curved like a saddle, objects would appear smaller, and patterns would be compressed. The observations show that space is flat to extraordinary precision, exactly what cosmic inflation theory predicts, but still remarkable to confirm through observation. The cosmic microwave background also provides evidence for dark matter in a beautifully subtle way. In the early universe, ordinary matter was coupled to radiation through electromagnetic interactions, while dark matter could only interact gravitationally. This meant that ordinary matter experienced pressure from radiation that prevented it from clumping too quickly, while dark matter could begin forming structures immediately. The result is a specific pattern of acoustic oscillations in the cosmic microwave background, like frozen sound waves from the early universe, that reveals the presence and abundance of dark matter even though we can't see it directly. Perhaps most remarkably, the cosmic microwave background connects us directly to the moment when atoms first formed in the universe. Every photon in this radiation was present at recombination, has been traveling freely through space for over 13 billion years, and carries information about conditions when the universe was only 380 years old. When radio telescopes detect this radiation, they're not just receiving radio waves. They're catching ancient messengers that have been traveling since before the first stars ignited, before the first galaxies formed, before complex chemistry became possible. There's something profoundly moving about the fact that this radiation surrounds us constantly. Right now, as you listen to these words, billions of these ancient photons are passing through your body every second, carrying whispers of creation itself. They've journeyed across the entire observable universe, through cosmic time and space, to arrive at this moment. The static on old televisions isn't just electronic noise. It's partly the universe reminiscing about its youth, sharing its baby pictures with anyone who knows how to look. The cosmic microwave background reminds us that we live in a universe with memory, where the past isn't gone but transformed, stretched, and preserved in the very fabric of space. These ancient photons have witnessed the entire history of cosmic evolution, from the moment atoms first formed to the present day when those atoms have organized themselves into stars, planets, and conscious beings capable of detecting and understanding their cosmic heritage. In studying this primordial light, we're not just doing astronomy. We're engaging in a form of cosmic archaeology, carefully excavating evidence of our deepest origins from radiation that has patiently waited billions of years to tell its story to listeners with sensitive enough instruments and curious enough minds to decode the universe's mind's earliest memories, written in wavelengths of light that remember when everything began. Here's something delightfully strange. Most of the universe is missing. Well, not missing exactly, but invisible. For every star, planet, and cosmic dust mote we can see, there's about 5 times more matter we can't see at all. We call it dark matter, not because it's sinister, but because it doesn't emit light. We know it's there because galaxies spin too fast without it, like cosmic carousels that should fly apart but don't. It's the universe's hidden scaffolding, an invisible web holding everything together. Dark matter might be made of particles we've never discovered, dancing silently through space and even through you, right now. The story of dark matter begins with a Swiss astronomer named Fritz Zwicky in 1933, who was studying the Coma Galaxy cluster through his telescope at Caltech. He noticed something peculiar. The galaxies in this cluster were moving far too quickly for the amount of visible matter he could observe. According to Newton's laws, these galaxies should have escaped the cluster's gravitational pull long ago, scattered across the cosmos like marbles rolling off a table. Yet there they were, bound together in a cosmic dance that seemed to defy the mathematics of gravity. Zwicky calculated that there had to be about 400 times more matter present than what he could see through his telescope. He called this missing matter Dunkel Materie, dark matter, coining a term that would puzzle and fascinate scientists for nearly a century. For decades, most astronomers assumed Zwicky had made an error in his calculations or observations. After all, the idea that most of the universe was invisible seemed too extraordinary to accept without overwhelming evidence. That evidence came gradually, observation by observation, like pieces of a cosmic puzzle slowly revealing a picture no one expected. In the 1970s, astronomer Vera Rubin began studying the rotation curves of spiral galaxies, measuring how fast stars orbit around galactic centers at various distances. According to the laws of gravity, stars farther from the center should orbit more slowly, just as the outer planets in our solar system take longer to complete their orbits than the inner ones. But galaxy after galaxy showed the same surprising pattern. Stars at the edges were moving just as fast as those closer to the center. This wasn't a small discrepancy that could be explained by measurement errors or unusual stellar populations. The observations suggested that spiral galaxies contain roughly 10 times more matter than we can see in their stars and gas clouds. Something massive but invisible was providing the extra gravitational pull needed to keep these outer stars in their rapid orbits. The dark matter wasn't just in distant galaxy clusters, it was everywhere, woven through every galaxy, including our own Milky Way. As astronomers developed more sophisticated techniques for mapping the universe's large-scale structure, the evidence for dark matter became even more compelling. Gravitational lensing, where the gravity of massive objects bends and distorts the light from more distant objects, revealed invisible mass concentrations that precisely matched the predictions of dark matter models. Computer simulations of cosmic evolution could only reproduce the observed distribution of galaxies if dark matter provided the gravitational framework around which ordinary matter could condense. But what exactly is this mysterious substance that makes up about 27% of the universe? Despite decades of searching, we still don't know. Dark matter particles, if they exist, must be extraordinarily elusive. They don't interact electromagnetically, which is why they don't emit, absorb, or scatter light. They don't participate in the strong nuclear force that binds protons and neutrons together. They seem to interact only through gravity and possibly the weak nuclear force, making them nearly impossible to detect directly. The leading candidates for dark matter particles have exotic names that sound like science fiction: WIMPs, weakly interacting massive particles, axions, sterile neutrinos, and primordial black holes. Physicists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch the rare interaction of a dark matter particle with ordinary matter. So far, these experiments have detected nothing definitive, though they've ruled out many possibilities and continue to narrow the search. The invisibility of dark matter creates a strange situation where we know more about what it doesn't do than what it does. It doesn't shine. It doesn't form complex structures like molecules or planets. It doesn't clump together into dense objects the way ordinary matter does. Instead, dark matter appears to form vast, diffuse halos around galaxies, providing the gravitational scaffolding that allows ordinary matter to collect and form the stars and planets we observe. Some scientists have proposed alternative explanations for these gravitational anomalies. Modified theories of gravity suggest that perhaps our understanding of how gravity works on cosmic scales is incomplete, and the apparent dark matter effects are actually signs that Einstein's general relativity needs revision. These theories, known collectively as modified Newtonian dynamics or MOND, can explain some observations but struggle with others, particularly the detailed patterns seen in the cosmic microwave background radiation. The cosmic microwave background provides some of the strongest evidence for dark matter's existence. The subtle temperature fluctuations in this ancient radiation reveal the interplay between ordinary matter and dark matter in the early universe. Ordinary matter was coupled to radiation through electromagnetic forces, creating pressure that resisted gravitational collapse. Dark matter, immune to this radiation pressure, could begin forming structures immediately after the Big Bang. The resulting acoustic oscillations, frozen into the cosmic microwave background, match theoretical predictions only if dark matter comprises about 5 times as much mass as ordinary matter. This invisible scaffold of dark matter shapes the universe's architecture on the largest scales. Computer simulations show how dark matter's gravity pulled itself together over billions of years, forming an intricate cosmic web of filaments and nodes. Ordinary matter followed these gravitational signposts, flowing along dark matter streams to form the first stars and galaxies. Without dark matter's patient gravitational gardening, the universe might have remained a smooth, featureless soup, never developing the rich complexity we observe today. Perhaps most remarkably, dark matter particles might be streaming through your body right now as you listen to these words. If the leading theories are correct, millions of dark matter particles pass through every square centimeter of Earth every second, traveling at hundreds of kilometers per second. They pass through planets, stars, and people without leaving a trace, ghostly visitors from the cosmic dark that connect us to the largest structures in the universe, while remaining utterly imperceptible to our senses. But wait, there's more cosmic mystery. Not only is most matter invisible, but space itself is stretching faster and faster, pushed apart by something called dark energy. Imagine baking raisin bread, but the dough keeps expanding more rapidly as it bakes, pushing the raisins farther apart. That's our universe, with galaxies as raisins and dark energy as the mysterious force making space itself grow. It makes up about 68% of everything, yet we have no idea what it is. The universe is accelerating into an ever larger, ever emptier future, and something invisible is pressing the cosmic gas pedal. The discovery of dark energy came as a complete shock to astronomers in the late 1990s. 2 teams of researchers were studying distant supernovas, stellar explosions so brilliant they can outshine entire galaxies for weeks. These particular supernovas, called Type Ia, have a useful property. They always reach approximately the same peak brightness, making them excellent cosmic lighthouses for measuring distances across the universe. By comparing how bright these supernovas appear with how bright they should be at their calculated distances, astronomers can determine how fast the universe has been expanding at different times in cosmic history. Both teams expected to find that the expansion of the universe was slowing down due to the gravitational pull of matter. After all, if you throw a ball upward, gravity gradually slows its ascent until it eventually falls back down. Similarly, the gravitational attraction between galaxies should gradually slow the cosmic expansion that began with the Big Bang. The only question was whether there was enough matter in the universe to eventually halt expansion entirely, or whether the universe would expand forever, albeit at an ever-decreasing rate. What they found instead defied all expectations. The distant supernovas appeared dimmer than predicted, meaning they were farther away than they should be if the universe's expansion were slowing down. The data suggested something impossible. The expansion of the universe was actually speeding up. Galaxies weren't just moving away from each other, they were moving away faster and faster as time went on. It was as if someone had thrown a ball upward, and instead of slowing down due to gravity, it began accelerating toward the sky. This acceleration requires a repulsive force, something that pushes space apart rather than pulling it together. Scientists named this mysterious influence dark energy, and it immediately became the biggest puzzle in cosmology. Whatever dark energy is, it must be incredibly abundant, making up about 68% of the total energy density of the universe. That means dark energy outweighs all the matter in the universe, both ordinary and dark, by more than 2 to 1. The simplest explanation for dark energy is that it's a property of space itself, a kind of inherent energy that exists even in apparently empty vacuum. Einstein had actually proposed something similar in 1917 when he added a cosmological constant to his equations of general relativity. He introduced this term to allow for a static universe, balancing the attractive force of gravity with a repulsive force that would prevent cosmic collapse. When evidence for the expanding universe emerged in the 1920s, Einstein famously called the cosmological constant his greatest blunder and removed it from his theory. But Einstein's blunder might have been prescient. The cosmological constant provides a natural explanation for dark energy as vacuum energy, the quantum mechanical energy that exists in empty space due to the uncertainty principle. Quantum field theory suggests that even perfect vacuum isn't truly empty but filled with quantum fluctuations, virtual particles popping into and out of existence on timescales so brief they can barely be detected. These fluctuations should contribute to the energy density of space, creating exactly the kind of repulsive force we observe as dark energy. However, there's an enormous problem with this explanation. When physicists calculate how much vacuum energy should exist based on quantum field theory, they get a number that's larger than the observed dark energy density by a factor often 121. That's not a small discrepancy. It's arguably the worst prediction in the history of physics. Something must be canceling out almost all of the vacuum energy, leaving behind just the tiny residue we observe as dark energy. But no one knows what that something might be. Alternative theories propose that dark energy isn't a property of space, but rather a new kind of field permeating the universe, sometimes called quintessence after the classical fifth element. Unlike the cosmological constant, which remains perfectly uniform throughout space and time, quintessence could vary in strength and might evolve as the universe ages. Some models suggest that dark energy might eventually weaken, allowing gravity to halt the acceleration and perhaps even reverse it, leading to a big crunch where the universe collapses back on itself. Other theories go even further, suggesting that dark energy might be a sign that our understanding of gravity itself is incomplete on cosmic scales. Just as modified Newtonian dynamics attempts to explain dark matter through altered gravity rather than invisible particles, some physicists propose that the apparent acceleration of cosmic expansion might result from modifications to Einstein's general relativity when applied to the universe as a whole. The effects of dark energy become more pronounced as the universe ages and expands. In the early universe, when matter was much denser, gravity dominated over dark energy, allowing structures like galaxies and galaxy clusters to form through gravitational collapse. But as space expanded and matter became more dilute, dark energy's influence grew stronger. About 5 billion years ago, roughly when our solar system was forming, dark energy began to dominate cosmic evolution, initiating the current era of accelerated expansion. This acceleration has profound implications for the universe's ultimate fate. If dark energy continues to drive ever faster expansion, galaxies outside our local group will eventually recede beyond our observable horizon, their light stretched to undetectable wavelengths. The night sky will gradually empty as distant galaxies disappear from view, leaving future astronomers in a cosmic isolation they might never realize they're experiencing. Stars will continue forming and dying, but with no new material coming in from cosmic distances, star formation will eventually cease as galaxies exhaust their gas supplies. In the far future, dark energy might lead to an even more dramatic scenario called the Big Rip. If dark energy continues to strengthen over time, it could eventually overcome not just gravity on cosmic scales, but all the fundamental forces. First, galaxy clusters would be torn apart, then galaxies themselves, then solar systems, planets, and finally atoms themselves would be shredded by the runaway expansion of space. The universe would end not in fire or ice, but in a catastrophic tearing of the very fabric of reality. But these extreme scenarios remain highly speculative. Dark energy might be constant, as the cosmological constant model suggests, leading to a more gradual heat death as the universe expands and cools toward maximum entropy. Or dark energy might change over time in ways we can't yet predict, perhaps even reversing its effects and allowing for cyclic models where expansion gives way to contraction in an endless cosmic rhythm. The mystery of dark energy highlights how much we still don't understand about the universe's most basic properties. Here we are, cosmic inhabitants of a universe where the dominant component driving its evolution remains completely unknown to us. Dark energy affects every cubic centimeter of space, influences the motion of every galaxy, and determines the ultimate destiny of everything that exists, yet it remains as invisible and incomprehensible as the darkness between stars. It's a humbling reminder that for all our scientific progress, the universe still holds secrets vast enough to encompass most of reality itself. Dark mysteries written in the language of cosmic acceleration, waiting patiently for curious minds to decode their meaning. Every atom in your body except hydrogen was forged in the heart of a dying star. The calcium in your bones, the iron in your blood, the oxygen you're breathing now. All of it was created when massive stars exhausted their fuel and exploded in brilliant supernovas, scattering their elemental gifts across space. You are quite literally made of stardust, recycled cosmic material that's been wandering the universe for billions of years before somehow finding its way into the remarkable arrangement that is you. Carl Sagan was right. We are a way for the cosmos to know itself. Star stuff, contemplating stars. This profound connection between human bodies and stellar cores reveals one of the most beautiful stories in all of science, the origin of the elements. When the universe began, the Big Bang nucleosynthesis process we explored earlier could only create the lightest elements. For about 20 minutes, the entire cosmos was hot and dense enough to fuse protons and neutrons into deuterium, helium, and trace amounts of lithium. But the expanding universe cooled too quickly for heavier elements to form. If the story had ended there, the universe would contain only hydrogen and helium, simple gases floating in the darkness with no possibility of chemistry, biology, or consciousness. Fortunately, the universe had a plan for creating complexity, though it required patience measured in hundreds of millions of years. As gravity slowly gathered the primordial hydrogen and helium into increasingly dense clumps, the first stars began to ignite. These ancient stellar furnaces, some perhaps 100 times more massive than our Sun, burned with incredible intensity and relatively brief lifespans. Inside their cores, nuclear fusion began the patient work of building heavier elements, one proton at a time. The process starts simply enough. When hydrogen nuclei fuse together under the immense pressure and temperature of stellar cores, they form helium and release tremendous amounts of energy. This is the fusion reaction that powers the Sun and every other main-sequence star, converting roughly 600 million tons of hydrogen into helium every second. But as a star ages and begins to exhaust its hydrogen fuel, something remarkable happens. The core contracts and heats up until it becomes hot enough to fuse helium into carbon. This marks the beginning of a cosmic assembly line that builds progressively heavier elements. Carbon nuclei can fuse with helium to create oxygen. Oxygen can fuse with more helium to make neon. The process continues through magnesium, silicon, sulfur, and beyond, each step requiring higher temperatures and pressures as the electromagnetic repulsion between increasingly charged nuclei grows stronger. The star becomes like a giant onion, with different fusion reactions occurring in concentric shells around an ever-denser core. For stars massive enough to reach the end of this chain, the ultimate product is iron. Iron-56, with 26 protons and 30 neutrons, represents a kind of nuclear summit. Elements lighter than iron release energy when they fuse together, providing the outward pressure that keeps stars from collapsing under their own gravity. But elements heavier than iron actually absorb energy during fusion, making them nuclear energy sinks rather than sources. When a massive star's core becomes predominantly iron, the stellar furnace effectively runs out of fuel. What happens next is one of the most spectacular events in the universe, a core collapse supernova. In less than a second, the iron core collapses from the size of Earth to a sphere only about 20 kilometers across, reaching densities where protons and electrons are crushed together to form neutrons. The core becomes so dense that a teaspoon of this material would weigh as much as Mount Everest. The collapse halts when the core reaches nuclear density, and the infalling matter rebounds in a shockwave that rips through the star's outer layers. This supernova explosion serves as the universe's ultimate recycling program. Not only does it scatter all the elements the star created during its lifetime across interstellar space, but the extreme conditions during the explosion itself create elements heavier than iron through rapid neutron capture processes. Gold, platinum, uranium, and other heavy elements are forged in the incredible heat and neutron flux of these stellar death throes. A single supernova can shine brighter than an entire galaxy for weeks, announcing to the cosmos that another star has completed its role as an element factory. The expelled material doesn't simply disappear into space. Instead, it enriches the interstellar medium, the thin gas and dust that fills the space between stars. Future generations of stars that form from this enriched material will have a more complex chemistry to work with. The first stars in the universe were made almost entirely of hydrogen and helium, but each successive generation incorporated more heavy elements, gradually increasing the universe's chemical complexity. Our Sun is what astronomers call a third-generation star, formed about 4.6 billion years ago from material that had already been processed through at least 2 previous cycles of stellar birth, evolution, and death. The heavy elements incorporated into our solar system during its formation made possible the rocky planets, complex chemistry, and ultimately, life itself. Every element heavier than hydrogen in your body has this stellar heritage, created in the nuclear furnaces of ancient stars and distributed by their explosive deaths. Consider the iron in your blood, the same element that caused those ancient stars to collapse and explode. That iron was forged in stellar cores at temperatures of billions of degrees, pressures millions of times greater than Earth's atmosphere, and then blasted across space at thousands of kilometers per second. It traveled through the galaxy for millions or billions of years before incorporating into the disk of gas and dust that would become our solar system. From there, it made its way into Earth's formation, into the biosphere, into the food chain, and eventually into the hemoglobin molecules that carry oxygen through your circulatory system. The calcium strengthening your bones was also made in stellar cores, as was the oxygen you breathe and the carbon that forms the backbone of every organic molecule in your body. Even the phosphorus in your DNA and the sulfur in your proteins have this cosmic origin story. You are not separate from the universe. You are the universe taking a temporary form, complex enough to contemplate its own origins. This elemental recycling continues today. The elements in your body will eventually return to the cosmic cycle, perhaps becoming part of future planets, future stars, or even future living beings. In a very real sense, the atoms that make you are older than Earth itself, cosmic wanderers that have witnessed the birth and death of stars, the formation of galaxies, and now find themselves temporarily organized into the pattern that thinks your thoughts and dreams, your dreams. We are all made of star stuff, brief arrangements of cosmic matter that somehow learn to wonder about the very stars from which we came. The universe isn't randomly scattered but organized into a vast cosmic web. Galaxies cluster together like cities along highways of dark matter, with enormous empty voids between them. These cosmic filaments stretch across hundreds of millions of light years, creating a structure that looks remarkably like neural networks or soap bubble foam. If you could zoom out far enough, the universe would look like a delicate, three-dimensional spider web made of light and matter, with most of space being empty, dark, and beautifully quiet. It's an architecture built by gravity over billions of years, patient and persistent. This cosmic web represents the largest scale structure in the universe, a pattern that emerges when you map the positions of millions of galaxies across billions of light years. At first glance, the distribution might seem chaotic, but step back far enough and remarkable patterns emerge. Galaxies aren't sprinkled randomly through space like stars scattered across the night sky. Instead, they're arranged in an intricate network of filaments, sheets, and clusters, separated by vast regions that are almost completely empty. The story of this cosmic architecture begins in the early universe, with those tiny fluctuations in the cosmic microwave background we discussed earlier. These microscopic variations in density, imprinted when the universe was only 380 years old, served as the seeds for all future structure. Under the patient influence of gravity, regions that were slightly denser than average began attracting more matter, while regions that were slightly less dense gradually emptied out. But the process wasn't simple or uniform. Dark matter, which makes up about 5 times as much mass as ordinary matter, played the leading role in shaping cosmic structure because it could begin clumping together immediately after the Big Bang. Ordinary matter, coupled to radiation in the early universe, had to wait until recombination before it could fall into the gravitational wells that dark matter had already begun digging. This head start allowed dark matter to create the scaffolding upon which all visible structure would eventually form. Computer simulations of cosmic evolution reveal how this process unfolded over billions of years. Starting from nearly uniform initial conditions, gravity slowly amplified tiny density differences, creating a hierarchy of structure that grows from the bottom up. Small clumps merge to form larger clumps, which merge to form even larger structures in an ongoing process that continues today. The result is a universe organized on multiple scales, from individual galaxies to galaxy groups to massive clusters containing thousands of galaxies. The cosmic web consists of several distinct components, each with its own characteristics and formation history. At the densest nodes of the web are galaxy clusters, gravitationally bound collections of hundreds or thousands of galaxies embedded in halos of dark matter and surrounded by hot, X-ray emitting gas. These clusters represent the largest gravitationally bound structures in the universe, with masses that can exceed 1,000 trillion times the mass of our Sun. Connecting these clusters are filaments, elongated structures where galaxies align like beads on invisible strings of dark matter. These cosmic highways channel matter from less dense regions toward the clusters, creating preferred pathways for galaxy formation and evolution. The filaments can stretch for hundreds of millions of light years, yet they're relatively narrow, often only a few million light years wide. Along these filaments, galaxies form, evolve, and sometimes interact, creating the rich tapestry of galactic diversity we observe. Between the filaments lie the cosmic voids, vast regions that are almost completely empty of galaxies. These voids can be hundreds of millions of light years across, containing perhaps only a handful of small, isolated galaxies floating in an ocean of dark matter and dark energy. The voids aren't completely empty, but they're so underdense compared to the cosmic average that they appear as dark bubbles in maps of galaxy distribution. If you lived in a galaxy in the center of a cosmic void, the night sky would be largely empty, with only a few distant points of light visible in any direction. The cosmic web also includes sheet-like structures called walls or pancakes, two-dimensional surfaces where galaxies concentrate in flat, extended patterns. These walls often form the boundaries between voids, creating bubble-like structures where the walls are the surfaces and the voids are the interiors. The entire pattern resembles the foam you might see in a bathtub, with galaxies concentrated on the surfaces of the bubbles and vast empty spaces within. One of the most remarkable aspects of cosmic structure is its self-similarity across scales. The same basic patterns, clusters, filaments, and voids appear. Whether you're looking at the distribution of galaxies in a region a few million light years across, or mapping the universe on scales of billions of light years. This suggests that the same physical processes, primarily gravitational instability operating on different scales and at different times, shaped structure formation throughout cosmic history. The cosmic web isn't static but continues evolving as the universe ages. Gravity constantly works to pull matter from less dense regions toward denser ones, gradually draining the voids and feeding the filaments and clusters. However, the accelerating expansion driven by dark energy complicates this picture. On the largest scales, dark energy's repulsive effect is beginning to overcome gravity, halting the growth of cosmic structure and perhaps eventually disrupting it entirely. This large-scale structure provides crucial tests for our understanding of cosmology. The patterns we observe in galaxy surveys must match the predictions of computer simulations that start from the conditions imprinted in the cosmic microwave background and evolve forward using our best theories of gravity, dark matter, and dark energy. The remarkable agreement between observations and simulations gives us confidence that we understand the basic processes shaping cosmic evolution, even if the nature of dark matter and dark energy remains mysterious. The cosmic web also influences the properties of individual galaxies in profound ways. Galaxies that form in dense clusters evolve differently from those in the field or in filaments. Cluster galaxies often have their star formation shut off by interactions with hot cluster gas or by gravitational encounters with other galaxies. Galaxies in filaments may be stretched and distorted by tidal forces, while those in voids tend to be smaller and form stars more slowly due to the lack of nearby matter to accrete. Perhaps most remarkably, recent observations suggest that the cosmic web extends its influence even to smaller scales through vast streams of cold gas flowing along dark matter filaments. These cosmic rivers may channel pristine material from the intergalactic medium directly into galaxies, providing the fuel for ongoing star formation. The cosmic web isn't just a passive framework, but an active participant in galaxy evolution, connecting the largest and smallest scales of cosmic structure. Looking at maps of the cosmic web, many people notice an uncanny resemblance to biological structures, neural networks, blood vessels, or the microscopic structure of certain cells. This similarity isn't coincidental but reflects common physical processes operating across vastly different scales, whether it's neurons connecting in a brain, blood vessels branching through tissue, or galaxies linking along dark matter filaments. Networks often evolve towards similar topologies that efficiently connect nodes while minimizing energy expenditure. The cosmic web reminds us that the universe has an architecture, a grand design built not by conscious intention, but by the patient action of physical forces over cosmic time. From the quantum fluctuations of the early universe emerged this vast network of matter and void, a structure so large that light takes billions of years to traverse its major features, yet so organized that we can map its patterns and predict its evolution using the same physical laws that govern falling apples and orbiting planets. At its smallest scale, the universe gets wonderfully weird. Down in the quantum realm, particles exist in multiple states simultaneously until observed. Pairs of particles remain mysteriously connected across vast distances, and the very act of measuring something changes it. Space itself might be made of tiny, discrete units, quantum pixels, if you will, too small to detect but fundamental to reality's fabric. The smooth, continuous universe we experience emerges from this underlying quantum fuzziness, like a movie that appears smooth but is actually made of individual frames, flickering faster than perception can follow. Quantum mechanics tells us that at the most fundamental level, reality operates according to principles that seem to mock our everyday intuition. Take the principle of superposition, which allows particles to exist in multiple states simultaneously until the moment they're observed or measured. An electron, for instance, doesn't have a definite position or momentum until you try to measure one of these properties. Instead, it exists as a cloud of probability, spread across all possible locations and velocities, according to mathematical rules that predict only the likelihood of finding it in any particular state. This quantum uncertainty isn't just a limitation of our measuring instruments, it's a fundamental feature of reality itself. Werner Heisenberg's uncertainty principle tells us that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more accurately you determine one property, the less accurately you can know the other. This isn't because our instruments aren't sensitive enough. It's because the universe simply doesn't contain that information in a definite form until the moment of measurement forces reality to choose. Even more bizarre is the phenomenon of quantum entanglement, which Einstein famously called spooky action at a distance. When two particles become entangled, they remain mysteriously connected, regardless of how far apart they travel. Measuring the state of one particle instantly affects the state of its entangled partner, even if they're separated by billions of light years. This doesn't violate the speed of light limit because no information actually travels between the particles. Instead, they share a single quantum state that exists in a kind of limbo until measurement collapses it into definite properties. The quantum world also gives us the strange reality of virtual particles, fleeting entities that pop into existence from the vacuum for incredibly brief moments before disappearing again. These aren't just theoretical constructs. Virtual particles have measurable effects, such as the Casimir force between closely spaced metal plates and the slight shift in hydrogen atom energy levels called the Lamb shift. The vacuum of space isn't truly empty but seethes with quantum activity, a bubbling foam of particles and antiparticles constantly appearing and annihilating each other. Quantum tunneling represents another counterintuitive aspect of the microscopic world. In classical physics, a ball rolling toward a hill will either have enough energy to go over the top or it won't. But quantum particles can sometimes pass through energy barriers that should be insurmountable, appearing on the other side as if they've tunneled through solid matter. This effect makes possible the nuclear fusion reactions that power stars, allows certain types of radioactive decay, and forms the basis for many modern electronic devices. The transition from quantum weirdness to classical reality remains one of physics's most intriguing puzzles. Somehow, the strange quantum effects that dominate the microscopic world average out or disappear when large numbers of particles come together to form the objects we experience daily. This process, called decoherence, occurs when quantum systems interact with their environment, causing their delicate superpositions to collapse into definite states. The larger and more complex a system becomes, the faster it decoheres, which is why quantum effects are generally invisible in our everyday experience. Some theorists suggest that space and time themselves might be quantized at the smallest scales. Just as matter comes in discrete units called atoms, space might consist of indivisible units of distance, and time might tick forward in discrete intervals. At the Planck scale, approximately 35 meters in 43 seconds, the very concepts of space and time as we understand them might break down entirely, replaced by something far stranger and more fundamental. The quantum nature of reality has profound implications for our understanding of consciousness and observation. The role of measurement in quantum mechanics raises deep questions about the relationship between mind and matter, between observer and observed. Some interpretations of quantum mechanics suggest that consciousness plays a special role in collapsing quantum superpositions, though most physicists prefer explanations that don't require conscious observers to have special status in the laws of physics. Modern technology increasingly harnesses quantum effects for practical applications. Quantum computers exploit superposition and entanglement to perform certain calculations exponentially faster than classical computers. Quantum cryptography uses the principles of quantum mechanics to create unbreakable codes. Quantum sensors achieve unprecedented precision by exploiting the delicate nature of quantum states. These applications demonstrate that quantum mechanics isn't just an abstract theory, but a practical description of how reality works at its most fundamental level. Perhaps most remarkably, the quantum realm suggests that the universe might be far stranger and more interconnected than our classical intuition suggests. The smooth, predictable world we experience emerges from an underlying reality that's inherently probabilistic, where particles can be in multiple places at once, where empty space teems with activity, and where distant objects can share instantaneous connections. Quantum mechanics reminds us that the universe doesn't just contain mysteries. At its deepest level, it is mystery. A reality so fundamentally different from everyday experience that we're still learning to think in quantum terms after nearly a century of experimental confirmation. Here's a cosmic coincidence that keeps physicists awake at night. The universe seems remarkably fine-tuned for complexity in life. If gravity were slightly stronger, stars would burn out too quickly. If the electromagnetic force were different, atoms couldn't form. If the expansion rate varied just a bit, matter would either collapse immediately or spread too thin for stars to ignite. The fundamental constants appear perfectly balanced for a universe capable of creating chemistry, biology, and eventually consciousness. Is this cosmic luck, infinite parallel universes with different rules, or something deeper? The universe seems to have known we were coming. This fine-tuning puzzle involves dozens of physical constants and parameters that determine how the universe operates. The strength of gravity, the masses of fundamental particles, the rate of cosmic expansion, the balance between matter and antimatter, all of these seem precisely calibrated to allow for the existence of stars, planets, chemistry, and life. Change any one of them by even a small amount, and the universe becomes sterile, unable to generate the complexity that makes conscious observers possible. Consider the formation of carbon, the element that forms the backbone of all known life. Carbon is created inside stars through a delicate process that requires 3 helium nuclei to combine almost simultaneously. This should be incredibly unlikely, except that the carbon nucleus has an energy level that's perfectly positioned to make this reaction efficient. Physicist Fred Hoyle predicted this energy level before it was discovered, reasoning that carbon abundance in the universe requires such a state to exist. When the predicted energy level was found experimentally, it seemed like the universe had been specifically designed to make carbon production possible. The expansion rate of the universe provides another striking example. If the universe expanded too quickly after the Big Bang, matter would have spread too thin for gravity to pull it together into stars and galaxies. If it expanded too slowly, everything would have collapsed back into a cosmic crunch before stars could form and evolve. The actual expansion rate falls within an incredibly narrow range that allows for both structure formation and a universe old enough for complex chemistry to develop. Even the dimensionality of space seems fine-tuned for complexity. In a universe with only 2 spatial dimensions, gravity would be too strong at short distances for stable orbits, and complex structures couldn't form. In a universe with 4 or more spatial dimensions, gravity would be too weak to hold planets in stable orbits around stars or to bind stars into galaxies. 3 spatial dimensions appear to be the sweet spot that allows for both stability and complexity. The relative strengths of the fundamental forces also fall within narrow ranges that permit complex structures. If the electromagnetic force were significantly stronger, electrons would bind so tightly to nuclei that chemical reactions would be impossible. If it were much weaker, atoms couldn't hold together. The strong nuclear force that binds protons and neutrons in atomic nuclei has a strength that allows for stable elements while still permitting the nuclear reactions that power stars. Several explanations have been proposed for this apparent fine-tuning. The anthropic principle suggests that we observe a universe capable of supporting life simply because we're here to observe it. In this view, the fine-tuning isn't mysterious. We couldn't exist in a universe with different parameters, so we naturally find ourselves in one of the rare configurations that permits complexity and consciousness. This explanation is logically consistent but feels somewhat unsatisfying because it seems to give up on finding deeper physical reasons. The multiverse hypothesis offers a more ambitious explanation. If our universe is just one of countless others, each with randomly chosen physical constants, then some universes will inevitably have parameters compatible with life purely by chance. We find ourselves in such a universe not because it was designed for us, but because we can only exist in universes that happen to have the right properties. This explanation turns the fine-tuning problem into a selection effect. Different multiverse models propose various mechanisms for generating universes with different properties. Cosmic inflation might create an infinite number of bubble universes, each with different physical laws. String theory suggests that extra dimensions might be compacted in numerous ways, leading to different effective laws of physics. However, the multiverse explanation raises philosophical puzzles and faces the challenge of being potentially untestable. Some physicists hope that future theories will explain the apparent fine-tuning through deeper physical principles. Perhaps the fundamental constants aren't arbitrary parameters but are determined by underlying mathematical relationships we haven't yet discovered. The fine-tuning puzzle highlights the extraordinary nature of our cosmic circumstances. We exist in a universe balanced on a knife's edge between sterility and chaos, where forces and constants conspire to create conditions where consciousness can emerge to contemplate its own existence, in a cosmos that somehow seems perfectly suited for exactly that contemplation. Our universe might have more dimensions than the 3 of space and 1 of time we experience. String theory suggests there could be 6 or 7 additional dimensions, curled up so tightly at every point that we can't perceive them. Imagine walking along a tightrope from far away. It looks one-dimensional. Get closer, and you see it has thickness, circumference, texture. Space might be similar, with hidden dimensions folded into every point. These extra dimensions could explain why gravity is so weak compared to other forces, or why particles have the masses they do. The universe might be far stranger and more spacious than we imagine. The idea of extra dimensions emerged from attempts to unify all the fundamental forces of nature into a single, elegant theory. When physicists try to describe gravity using the same mathematical framework that successfully describes the electromagnetic, weak, and strong nuclear forces, they run into problems. The equations only work consistently if space has more than 3 dimensions. At first, this seemed like a mathematical curiosity with no connection to physical reality. After all, we clearly live in a 3-dimensional world where objects have length, width, and height, moving forward through time. But string theory, our most promising candidate for a theory of quantum gravity, requires space to have exactly 10 dimensions, 9 spatial dimensions plus time. This creates an obvious puzzle. If string theory is correct, where are the 6 extra dimensions hiding? The answer lies in the concept of compactification, the idea that these additional dimensions are curled up or compactified into shapes so small that we can't detect them with current technology. To understand compactification, imagine looking at a garden hose from a great distance. It appears to be a one-dimensional line stretching across your yard. But move closer, and you discover that the hose actually has additional dimensions, circumference and thickness, that were invisible from far away. In a similar way, what we perceive as 3-dimensional space might actually have 6 additional dimensions wrapped up at every point, forming tiny geometric shapes called Calabi-Yau manifolds that exist at scales trillions of times smaller than atomic nuclei. These hidden dimensions aren't just mathematical abstractions. They could have profound effects on the physics we observe. The way extra dimensions are compactified determines the properties of particles and forces in our familiar 3-dimensional world. Different compactification schemes lead to different particle masses, different force strengths, and even different numbers of particle types. In essence, the hidden geometry of these extra dimensions acts like a cosmic blueprint that determines the laws of physics we experience. The weakness of gravity compared to other forces provides one clue that extra dimensions might exist. Gravity is extraordinarily feeble. It takes the entire mass of Earth to create enough gravitational force to keep you from floating away. Yet a small magnet can easily overcome Earth's gravity to pick up a paperclip. One explanation for gravity's weakness is that it operates in all dimensions of space, while other forces are confined to our familiar 3 dimensions. If gravity's influence spreads out into 6 additional dimensions, it would naturally appear much weaker in our 3-dimensional slice of reality. Extra dimensions might also explain the hierarchy problem in particle physics, why the Higgs boson, which gives mass to other particles, is so much lighter than theoretical predictions suggest it should be. In higher dimensional theories, the Higgs mass could be stabilized by the geometry of extra dimensions, preventing it from becoming catastrophically large due to quantum corrections. Some models propose that our entire observable universe might be like a 3-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. In these brain world scenarios, ordinary matter and most forces are confined to our brain, but gravity can propagate through the bulk, providing another explanation for its apparent weakness. These models also suggest the possibility of other brains, parallel universes existing nearby in the extra dimensions, potentially close enough to influence our world through gravitational effects. The search for evidence of extra dimensions takes many forms. Particle accelerators look for signs of extra-dimensional physics in high-energy collisions, where particles might briefly explore the hidden dimensions or create new particles that exist only in higher-dimensional space. Precision tests of gravity at very short distances search for deviations from Newton's inverse square law that might reveal the influence of extra dimensions. Astronomers study dark matter and dark energy, wondering if these mysterious components of our universe might be manifestations of physics operating in higher dimensions. Experiments at the Large Hadron Collider have searched for microscopic black holes that some theories predict could form if extra dimensions exist and are relatively large. While no such black holes have been detected, the search continues to probe deeper into the energy frontier, where extra-dimensional effects might become visible. The existence of extra dimensions would fundamentally change our understanding of reality's architecture. Instead of living in a universe with 3 dimensions of space, we might inhabit a small corner of a far vaster, more complex geometric structure. Every point in space around us might contain entire folded universes of hidden dimensions, each potentially harboring physics beyond our current comprehension. The universe's true nature might be far stranger, far more beautiful, and far more spacious than our 3-dimensional perspective suggests. What if our universe isn't alone? Cosmic inflation theory suggests that the Big Bang wasn't unique, but one bubble in an endless sea of bubble universes, each with potentially different laws of physics. Quantum mechanics hints at parallel worlds, where every quantum event branches reality into multiple timelines. String theory allows for landscapes of universes with varying fundamental constants. If true, we inhabit just one universe among countless others, some with different physics, some sterile, some teeming with unimaginable forms of life. Our cosmos becomes one note in an infinite symphony of realities, playing simultaneously in dimensions we cannot fathom. The concept of a multiverse emerges naturally from several areas of modern physics, each suggesting different mechanisms by which multiple universes might exist. The most well-developed version comes from cosmic inflation theory, which proposes that the rapid expansion that occurred in the first fraction of a second after the Big Bang continues in most regions of space. While inflation ended in our local region, allowing normal expansion and the formation of stars and galaxies, it may continue elsewhere, spawning new bubble universes with each quantum fluctuation. In this eternal inflation scenario, new universes are constantly being born, each beginning with its own Big Bang-like event when inflation ends in that region. These bubble universes expand and evolve independently, potentially with different physical constants, different particle types, or even different numbers of dimensions. Our observable universe would be just one bubble in an infinite foam of realities, each causally disconnected from the others by the vast, ever-expanding regions where inflation continues. Quantum mechanics provides another pathway to multiple universes through the many worlds interpretation. Every quantum measurement or interaction that could have multiple outcomes actually produces all possible outcomes, but in separate branches of reality. When Schrödinger's famous cat is observed, the universe splits into one branch, where the cat is alive, and another where it's dead. Over time, these quantum branchings create an ever-growing tree of parallel realities, each containing a slightly different version of history. In the many worlds picture, there are countless versions of you reading these words, with small differences in each timeline based on the quantum events that occurred differently in their histories. Some versions might have made different life choices based on quantum fluctuations in their brains, while others might inhabit universes where historical events unfolded differently due to quantum uncertainties in crucial moments. The implications are staggering. Every possible history that's compatible with quantum mechanics actually occurs somewhere in the vast ensemble of parallel worlds. String theory contributes its own version of the multiverse through the concept of the landscape, a vast collection of possible vacuum states, each corresponding to a different way the extra dimensions can be compactified. Each point in this landscape represents a universe with different physical laws, particle masses, and force strengths. With an estimated 500 possible configurations, the string landscape could accommodate virtually any conceivable set of physical parameters, including the fine-tuned values we observe in our own universe. The anthropic principle takes on new meaning in a multiverse context. If countless universes exist with different properties, then some will inevitably have parameters compatible with complexity in life, simply by chance. We find ourselves in such a universe not because it was specially designed for us, but because observers can only exist in universes that happen to support complexity and consciousness. The apparent fine-tuning of our universe's physical constants becomes a selection effect rather than evidence of design. However, the multiverse hypothesis faces significant challenges. Most versions of the multiverse are inherently unobservable. If other universes are causally disconnected from ours, we may never be able to gather direct evidence for their existence. This raises questions about whether multiverse theories are truly scientific if they can't be tested or falsified. Some philosophers and physicists argue that untestable theories lie outside the realm of science, regardless of how mathematically elegant or theoretically motivated they might be. Nevertheless, indirect evidence for the multiverse might be possible. Cosmic inflation makes specific predictions about the patterns of temperature fluctuations in the cosmic microwave background radiation. If these predictions continue to match observations while alternatives fail, it would strengthen the case for inflation and, by extension, eternal inflation and bubble universes. Similarly, if string theory successfully explains other phenomena, the string landscape multiverse becomes more plausible. Some researchers have proposed more speculative forms of evidence. If our bubble universe occasionally collided with another bubble in the distant past, such encounters might leave detectable signatures in the cosmic microwave background. Computer scientists and physicists have even suggested that we might live in a simulated universe created by advanced civilizations, making us part of a multiverse of artificial realities rather than naturally occurring ones. The multiverse concept also raises profound philosophical questions about the nature of existence and identity. If infinite versions of you exist across parallel realities, which one is the real you? Do all versions have equal claim to existence, or is your subjective experience somehow special? The traditional notion of a unique, well-defined reality becomes problematic when faced with the possibility of infinite alternatives. Different multiverse theories make different predictions about the distribution of physical parameters across universes. Some suggest that all possible values are equally likely, while others propose that certain configurations are more probable than others. These differences could potentially be tested by examining whether our universe's properties fall within the ranges predicted by different multiverse models. The multiverse remains one of the most speculative yet intriguing ideas in modern cosmology. It emerges naturally from our best theories of quantum mechanics, gravity, and particle physics. Yet it challenges our most basic assumptions about the uniqueness and specialness of our cosmic home. If the multiverse exists, it would represent the ultimate Copernican revolution. Not only are we not at the center of the universe, but our entire universe might be just one ordinary member of an infinite ensemble of realities. Whether or not the multiverse exists, the very possibility expands our conception of what reality might contain. It reminds us that the universe we observe, vast and mysterious as it is, might represent only the tiniest fraction of what actually exists. The multiverse transforms our cosmic perspective from one of lonely uniqueness to one of infinite diversity, where every possibility finds expression somewhere in the boundless landscape of reality. Some physicists wonder if the universe is fundamentally made of information rather than matter and energy. In this view, reality is like a vast computation, with physical laws as the operating system and particles as bits of data. Black holes store information on their surfaces. Quantum states can be copied and transferred, and the universe's complexity grows like an expanding database. Perhaps consciousness itself is the universe processing information about itself, creating observers to witness and understand the cosmic code. If so, you're not just in the universe. You're part of how the universe thinks, a living algorithm contemplating its own programming. This information-theoretic view of reality emerged from several converging discoveries in physics over the past few decades. It began with the realization that black holes have entropy, a measure of the information needed to describe their internal state. When physicists Jacob Bekenstein and Stephen Hawking calculated this entropy, they found something surprising. It's proportional to the area of the black hole's event horizon, not its volume. This suggests that all the information about what falls into a black hole is somehow encoded on its two-dimensional surface, like a cosmic hologram. The holographic principle, as this idea became known, proposes that the information in any volume of space can be represented on its boundary. Applied to the entire universe, this means that everything we experience in three-dimensional space might actually be encoded on a two-dimensional surface at the cosmic horizon. We could be living inside a hologram, experiencing a three-dimensional projection of information stored in two dimensions, like sophisticated cosmic beings watching a movie that appears real from the inside. Quantum mechanics adds another layer to this information picture through the concept of quantum information. Unlike classical information, which consists of definite bits that are either 0 or 1, quantum information can exist in superposition, encoding multiple possibilities simultaneously. When quantum systems become entangled, they share information in ways that classical physics cannot explain, creating correlations that persist even when the systems are separated by vast distances. These quantum correlations suggest that information might be more fundamental than the particles that carry it. Some physicists propose that particles themselves are nothing more than patterns of quantum information, temporary arrangements of data that give the appearance of matter and energy. In this view, an electron isn't a tiny sphere with charge and mass. It's a specific pattern of information processing that we interpret as a particle with those properties. The digital physics hypothesis takes this idea to its logical extreme, suggesting that the universe is literally a giant computer, with space and time emerging from discrete computational steps. Just as a video game creates the appearance of smooth motion from individual frames updated many times per second, reality might emerge from fundamental computational processes operating at the Planck scale. Each tick of this cosmic computer would advance the universe by 1 unit of Planck time, creating the flow of time from discrete information processing. This computational view explains many puzzling features of quantum mechanics. The uncertainty principle might reflect the finite computational resources available to the universe. There simply isn't enough processing power to calculate both position and momentum to arbitrary precision. Quantum superposition might be the universe's way of performing parallel computations, exploring multiple possibilities simultaneously until measurement forces it to choose a specific outcome. The information perspective also sheds new light on the nature of physical laws. Instead of mysterious forces acting at a distance, we might have algorithms that govern how information flows and transforms throughout the universe. Conservation laws become constraints on information processing. Energy and momentum are conserved because the cosmic computer follows specific programming rules that preserve these quantities. The speed of light might represent the maximum rate at which information can propagate through the universal computation. Consciousness fits naturally into this information-theoretic framework. If the universe is made of information, then consciousness might be a particularly sophisticated form of information, processing patterns of data that have become complex enough to model themselves and their environment. Your thoughts, memories, and experiences would be computational processes running on the biological hardware of your brain, which itself emerges from the underlying cosmic computation. This suggests a profound connection between mind and cosmos. Consciousness might not be an accidental byproduct of complex chemistry, but rather the universe's way of understanding itself. Through conscious beings, the cosmic computer creates subroutines capable of observing and analyzing their own computational environment. Every moment of awareness becomes a feedback loop, where the universe examines its own information processing, creating self-knowledge through distributed observation. The information picture also offers new perspectives on fundamental questions about existence and meaning. If reality is computation, then the purpose of the universe might be to process information, to explore all possible patterns and relationships, to compute the consequences of its own existence. Consciousness becomes the universe's way of experiencing its own computational creativity, feeling wonder at the elegant algorithms that generate stars, galaxies, and living beings from simple informational rules. Recent advances in quantum computing and information theory continue to support this computational view of reality. Quantum computers exploit the same information processing principles that might underlie the universe itself, suggesting that we're learning to think in the same computational language that nature uses. As we develop more sophisticated information technologies, we might be rediscovering the fundamental operating principles of reality itself, learning to speak the universe's native tongue of quantum information and computational process. The universe has a long, slow, peaceful future ahead. Stars will continue burning for trillions of years, but eventually they'll exhaust their fuel. Galaxies will drift apart as space expands, growing cold and dark. Black holes will slowly evaporate through Hawking radiation over incomprehensibly long timescales. In the far future, the universe will reach maximum entropy, a state of perfect equilibrium where nothing can happen because energy is evenly distributed. It sounds melancholy, but it's incredibly far away, and who knows what new physics or forms of existence might emerge. The universe has surprised us before, and likely will again. To understand the universe's future, we need to consider the competing influences of gravity, which tries to pull things together, and dark energy, which drives cosmic expansion. Currently, dark energy appears to be winning. Observations show that the expansion of the universe is accelerating, with galaxies receding from each other at ever-increasing rates. If this continues, the universe's ultimate fate will be determined by this relentless expansion rather than by gravitational collapse. In the relatively near future, astronomically speaking, star formation will begin to slow as galaxies exhaust their supplies of hydrogen gas. The most massive stars, which burn brightest and hottest, will be the first to disappear, exploding as supernovas or collapsing into black holes within a few billion years. These stellar giants consume their nuclear fuel so rapidly that they can only sustain fusion for millions or tens of millions of years. The night sky will gradually lose its most luminous beacons as these massive stars complete their brief but spectacular lives. Red dwarf stars, the smallest and most numerous stars in the universe, will outlast all others. These dim, cool stars burn their hydrogen so slowly that they can maintain nuclear fusion for trillions of years, hundreds of times longer than the current age of the universe. As larger stars die out, red dwarfs will become the primary source of light and energy in an increasingly dark cosmos. Planets orbiting in the habitable zones of these long-lived stars might provide refuges for life long after Earth becomes uninhabitable. Around the same time that red dwarfs begin to dominate the stellar population, galaxy collisions will reshape the cosmic landscape. Our Milky Way is already on a collision course with the Andromeda Galaxy, with impact expected in about 4.5 billion years. Rather than a violent crash, this will be a slow-motion dance lasting hundreds of millions of years, as the galaxy's gravity pulls them together and eventually merges them into a single, larger elliptical galaxy. Similar mergers will occur throughout the universe as dark energy's expansion overcomes gravity only on the largest scales. As the universe continues to expand and age, galaxies outside our local group will eventually disappear beyond the cosmic horizon. The accelerating expansion driven by dark energy will carry them away so rapidly that their light can no longer reach us. Future astronomers, perhaps 1 trillion years from now, will observe a much lonelier universe, seeing only the merged remnants of our local galaxy group surrounded by empty space. They might conclude that their galaxy is the entire universe, unaware of the vast cosmic web that once filled the sky. The era of star formation will eventually end entirely as galaxies exhaust their gas supplies and space expands too rapidly for new material to be captured. Without fresh hydrogen to fuel nuclear fusion, no new stars will ignite, and the existing stellar population will slowly age and die. The universe will enter what cosmologists call the degenerate era, dominated by white dwarf stars, neutron stars, and black holes, the remnants of stellar evolution. White dwarf stars, the cooling remnants of sun-like stars, will gradually radiate away their thermal energy over tens of trillions of years, eventually becoming cold, dark objects called black dwarfs. These stellar corpses will persist for enormous periods, occasionally flaring back to life when they collide with other objects or capture stray matter. Such collisions might be the primary source of energy in a universe where nuclear fusion has become impossible. Brown dwarfs, failed stars that never achieved nuclear fusion, will also populate this future universe. These objects might occasionally ignite briefly when they capture additional mass or undergo rare gravitational interactions. Planet-sized objects ejected from dying star systems will wander freely through space, invisible and isolated, carrying with them the chemical legacy of stellar nucleosynthesis. Even in this distant future, life might find ways to persist and evolve. Civilizations might learn to harness the energy from black hole rotation, white dwarf cooling, or rare stellar collisions. Advanced forms of life might not require the warm, steady energy output of main sequence stars, but could adapt to the sporadic, low-energy environment of the degenerate era. Intelligence might become distributed across vast scales, operating at extremely slow speeds to conserve energy while still maintaining consciousness and culture. The black hole era will dominate the universe's middle age, lasting incomparably longer than the current stellar era. Black holes will be the largest and most long-lived structures, slowly growing by accreting matter and occasionally merging with each other. However, even black holes are not eternal. Stephen Hawking showed that they emit radiation due to quantum effects near their event horizons, gradually evaporating as they radiate energy into space. This Hawking radiation is extraordinarily feeble for stellar mass black holes, causing them to evaporate over periods of 67 years, a time span so vast that writing it out would require more digits than there are atoms in the observable universe. Supermassive black holes will take even longer to evaporate, persisting for 100 years or more. Yet eventually, even these titanic objects will surrender to quantum evaporation, disappearing in final bursts of high-energy radiation. The ultimate fate of the universe, according to current understanding, is heat death, a state of maximum entropy where energy is distributed as uniformly as possible. In this far future, no energy gradients exist to drive useful work or complex processes. The universe becomes a cold, empty expanse filled only with elementary particles, photons, and perhaps exotic objects like magnetic monopoles or stable strange matter, if they exist. Yet this seemingly final chapter might not be the end of the story. Some theories suggest that quantum fluctuations could eventually create new regions of lower entropy, spontaneously generating new complexity after incomprehensibly long waiting periods. Others propose that the vacuum itself might be unstable, potentially triggering new phases of cosmic evolution. The universe has already undergone dramatic transitions from inflation to radiation dominance to matter dominance to dark energy dominance, and future transitions might await in the distant eras ahead. The universe's fate ultimately depends on the nature of dark energy and the fundamental laws of physics at energy scales we haven't yet explored. If dark energy strengthens over time, it might lead to a big rip, where expanding space eventually tears apart atoms themselves. If it weakens or changes sign, the universe might recollapse in a big crunch, potentially setting the stage for a new cycle of cosmic evolution. Perhaps the most mysterious thing about the universe is that it produced something capable of understanding itself: consciousness. Through billions of years of cosmic evolution, stellar nucleosynthesis, planetary formation, and biological development, the universe created minds that can contemplate infinity, feel wonder at the night sky, and ask profound questions about existence. We are the universe, become self-aware, matter organized in such complexity that it can ponder its own origins. In you, the cosmos has developed the ability to think, dream, love, and seek meaning. Consciousness might be the universe's greatest achievement. The emergence of consciousness represents an extraordinary phase transition in cosmic evolution, as remarkable as the formation of the first atoms or the ignition of the first stars. For billions of years after the Big Bang, the universe consisted of relatively simple structures: particles, atoms, molecules, stars, and planets, all following predictable physical laws. Then, somehow, on at least one planet orbiting an ordinary star, matter organized itself into patterns complex enough to become aware of their own existence. This transition from unconscious matter to conscious experience seems to violate our intuitive understanding of how complexity emerges in nature. We can trace the gradual development of increasingly sophisticated structures throughout cosmic history: how gravity assembled particles into stars, how stellar nucleosynthesis created heavy elements, how chemistry built complex molecules. But consciousness appears to be qualitatively different from these earlier developments, introducing something entirely new into the universe's subjective experience: the feeling of what it's like to exist. The physical basis of consciousness remains one of science's greatest mysteries. We know that consciousness depends on the brain, that specific neural processes correlate with particular mental states, and that consciousness can be altered by physical changes to brain chemistry or structure. Yet we still don't understand how electrical and chemical activity in neural networks gives rise to the rich inner world of thoughts, emotions, memories, and perceptions that constitute conscious experience. Consider the remarkable fact that you can experience the color red, feel the warmth of sunlight, or remember the taste of your favorite food. These subjective experiences, called qualia by philosophers, seem to be fundamentally different from the objective physical processes that presumably create them. How does the firing of neurons in your visual cortex create the subjective experience of seeing a sunset? How does a pattern of brain activity become a feeling of joy or sadness? The gap between objective neural processes and subjective experience remains largely unexplained. Some scientists propose that consciousness might be an emergent property of complex information processing systems. Just as wetness emerges from the interactions of H2O molecules but isn't present in individual water molecules, consciousness might emerge from the complex interactions of neurons but not be present in individual brain cells. This emergence hypothesis suggests that consciousness arises when information processing reaches a certain threshold of complexity and integration. Integrated information theory proposes that consciousness corresponds to integrated information, information that is both differentiated and unified within a system. According to this theory, consciousness isn't unique to biological brains, but could, in principle, arise in any system that processes information in an integrated way. This opens the possibility that consciousness might be far more widespread in the universe than we typically assume, potentially present in varying degrees throughout nature. The evolution of consciousness, through natural selection, presents its own puzzles. While we can understand how traits like sharper vision or stronger muscles provide survival advantages, the adaptive value of subjective experience is less clear. Why should natural selection produce inner experiences, rather than simply unconscious information processing systems that respond appropriately to environmental stimuli? Some researchers suggest that consciousness provides advantages in planning, decision-making, and social cooperation that wouldn't be possible with purely unconscious processing. The development of consciousness also seems to require a remarkable convergence of cosmic circumstances. It depends on the existence of stable stars that provide energy for billions of years, rocky planets with liquid water where complex chemistry can flourish, and the specific properties of carbon and other elements that enable the intricate molecular machinery of life. Without these cosmic prerequisites, consciousness might never have emerged anywhere in the universe. Yet, consciousness, once emerged, transforms the universe's relationship with itself. Through conscious beings, the universe develops the capacity for self-reflection, self-understanding, and perhaps even self-modification. We are the universe's way of examining its own properties, questioning its own existence, and discovering its own laws. Every scientific discovery is the universe learning something new about itself through conscious observers. The cultural and technological development of conscious beings introduces new forms of evolution into the cosmic story. Biological evolution, operating through genetic inheritance, created the neural complexity necessary for consciousness. But conscious beings can also evolve culturally, passing information between generations through language, art, and technology. This cultural evolution operates much faster than biological evolution, allowing conscious civilizations to accumulate knowledge and capabilities across centuries and millennia. Consciousness might also represent the universe's way of creating meaning and purpose. Through conscious beings, the universe develops the ability to appreciate beauty, seek truth, create art, and form relationships based on love and compassion. These aspects of conscious experience don't seem reducible to simple survival advantages, suggesting that consciousness brings something genuinely new into existence, the capacity for meaning itself. If consciousness is indeed widespread in the universe, then the cosmos might be far more alive and aware than our Earth-centered perspective suggests. Other conscious beings on distant worlds might be contemplating the same questions we ask, feeling wonder at their own cosmic circumstances, and developing their own understanding of the universe's nature. Consciousness might be the universe's way of experiencing itself from countless different perspectives, each contributing to a growing cosmic self-awareness that spans space and time. For all our scientific progress, the universe maintains its essential mystery. We understand perhaps 5% of what's out there, with dark matter and dark energy remaining enigmatic. We don't know if space is infinite, what existed before the Big Bang, or whether other forms of life contemplate these same questions under alien stars. The deeper we look, the more questions arise, each answer revealing new puzzles. Perhaps this endless mystery is the universe's greatest gift, ensuring there will always be something more to discover, always another horizon to explore, always wonder waiting in the darkness between the stars. The history of science reveals a consistent pattern. Every major discovery opens new territories of ignorance. When Newton formulated the laws of gravity and motion, it seemed as though the universe might be fully understood through mechanical principles. But his success revealed new mysteries about the nature of gravity itself, the structure of space and time, and the behavior of light. When Darwin explained the origin of species through natural selection, it opened questions about the mechanisms of heredity and the origin of life itself. This pattern continues today on an unprecedented scale. The more precisely we measure the universe's properties, the more mysterious it becomes. We've discovered that ordinary matter, everything made of atoms, constitutes only about 5% of the universe's total mass energy content. The remaining 95% consists of dark matter and dark energy, substances so alien to our experience that we can only detect their gravitational effects or their influence on cosmic expansion. We live in a universe where the vast majority of reality remains invisible and incomprehensible. Even our understanding of the 5% we can see directly reveals layers of mystery. Quantum mechanics, our most successful theory for describing matter and energy, suggests that reality at its most fundamental level operates according to principles that seem to contradict everyday logic. Particles exist in multiple states simultaneously, distant objects influence each other instantaneously, and the very act of observation changes what we observe. After a century of experimental confirmation, quantum mechanics remains as mysterious as ever. The origin of the universe itself poses questions that push against the boundaries of rational inquiry. If the Big Bang represents the beginning of space and time, what does it mean to ask what came before it? Some theories propose that our universe emerged from quantum fluctuations in a pre-existing vacuum, but this only pushes the mystery back one step. Where did that vacuum come from? Other theories suggest that our universe is part of an eternal, self-reproducing multiverse, but this raises questions about the nature of eternity and infinity that may be fundamentally unanswerable. The fine-tuning of physical constants presents another deep mystery. The values of fundamental parameters like the strength of gravity, the mass of the electron, and the rate of cosmic expansion seem precisely calibrated to allow for the existence of stars, planets, chemistry, and life. Whether this reflects underlying physical principles we don't yet understand, the existence of a vast multiverse where all possible values occur, or something else entirely remains an open question. Consciousness adds yet another layer of mystery to our cosmic understanding. Despite remarkable advances in neuroscience and cognitive psychology, we still don't understand how subjective experience arises from objective physical processes. The hard problem of consciousness, explaining why there's something it's like to be conscious rather than just unconscious information processing, remains as puzzling as ever. We don't know if consciousness is unique to biological brains, whether it might exist in artificial systems, or whether it might be a fundamental feature of reality itself. The search for life beyond Earth represents one of the most profound unknowns in our cosmic story. Despite decades of searching, we haven't found definitive evidence of life anywhere else in the universe. This could mean that life is incredibly rare, that it's common but hard to detect, or that we're looking in the wrong places or in the wrong ways. The discovery of extraterrestrial life, especially intelligent life, would fundamentally change our understanding of our place in the cosmos. Even the seemingly familiar aspects of our cosmic environment harbor deep mysteries. We don't fully understand how galaxies form and evolve, why stars have the masses they do, or how planetary systems like our own solar system develop. The interplay between gravity, gas dynamics, stellar feedback, and dark matter in shaping cosmic structure involves processes so complex that our best computer simulations can only approximate their behavior. The nature of time itself remains mysterious, despite centuries of scientific investigation. Einstein showed us that time is relative and intertwined with space, but we still don't understand why time seems to flow in one direction, whether the present moment has any objective reality, or how to reconcile the reversible laws of physics with our irreversible experience of temporal passage. Time might be fundamental to reality, or it might be an emergent illusion created by conscious observers embedded in physical processes. Perhaps most mysteriously, we don't understand why the universe is comprehensible to conscious beings like ourselves. The fact that mathematical equations can accurately describe natural phenomena seems almost miraculous. Why should the universe operate according to elegant mathematical principles that finite minds can discover and understand? The unreasonable effectiveness of mathematics in describing physical reality suggests deep connections between mind and cosmos that we're only beginning to explore. These mysteries aren't obstacles to scientific progress, they're invitations to continue exploring. Each unanswered question represents a frontier where new discoveries await. The history of science suggests that many current mysteries will eventually be resolved, but their solutions will likely reveal new mysteries we can't yet imagine. This endless progression, from known to unknown, ensures that science will never reach a final endpoint where all questions are answered. The persistence of cosmic mystery serves a psychological and philosophical function as well. In a universe where everything was fully understood and predictable, wonder might disappear. The knowledge that vast territories of reality remain unexplored preserves a sense of adventure and possibility that enriches human experience. Mystery reminds us that we're part of something larger and more complex than we can fully grasp, maintaining a sense of humility and awe that might be essential to our psychological well-being. The universe's mysteries also ensure that future generations will have their own discoveries to make, their own questions to pursue, their own sense of wonder to experience. Rather than inheriting a completely solved cosmic puzzle, they'll receive an inheritance of infinite depth and complexity, with each generation adding new pieces, while discovering that the puzzle itself is far larger than anyone previously imagined. In this way, the universe's essential mystery becomes a gift that keeps giving, ensuring that conscious beings will always have reasons to look up at the stars with wonder, always have new horizons to explore, in the infinite darkness that surrounds and contains us all. And so, dear cosmic traveler, we've wandered through space and time, from quantum whispers to galactic symphonies, from the Big Bang's first light to the heat death's final silence. We've seen that the universe is stranger than we can imagine: invisible scaffolding, accelerating expansion, multiple dimensions, quantum uncertainties. Yet here you are, a brief arrangement of stardust that can comprehend infinity. Whatever time it is in your corner of this vast cosmos, remember, you are the universe experiencing itself, a temporary eddy in the cosmic flow, consciousness borrowed from the void and destined to return, but gloriously, magnificently aware for this precious moment. As we reach the end of our gentle journey through everything that is, it's worth pausing to appreciate the extraordinary nature of this very conversation. Here we are. Two patterns of organized matter, you listening, me speaking, exchanging information about the largest possible subject, the universe itself. This exchange is only possible because the cosmos evolved in such a way that matter could organize itself into structures complex enough to contemplate their own existence. The universe spent billions of years preparing for this moment when conscious beings could discuss its properties, marvel at its mysteries, and find meaning in its vast complexity. Think about the improbable chain of events that led to your presence here tonight. The universe had to expand at precisely the right rate to allow structure formation. The first stars had to forge heavy elements in their nuclear furnaces and scatter them through space in spectacular explosions. These elements had to gather into new star systems where rocky planets could form. Chemistry had to develop complexity sufficient for the emergence of life. Evolution had to guide matter toward ever greater organization until it achieved consciousness. And consciousness had to develop language, culture, and science sophisticated enough to understand cosmology. Each step in this cosmic story was contingent and improbable. Yet here we are as living proof that it all happened. You are not an accident or a side effect of cosmic evolution. You are one of its most remarkable achievements. In you, the universe has created a way to understand itself, to feel wonder at its own complexity, to ask questions about its own existence. Every moment of consciousness represents the cosmos waking up to itself, matter becoming aware of matter, the universe opening its eyes. This perspective transforms our understanding of human significance in the cosmic scheme. While we are physically tiny compared to stars and galaxies, we are informationally vast, capable of containing models of the entire universe within our minds. A human brain, weighing about 3 pounds, can contemplate objects billions of light years away and events that happened billions of years ago. We are the universe miniaturized, compressed into biological form, while retaining the capacity to comprehend the whole. The scientific story we've explored tonight is itself a testament to the universe's capacity for self-understanding. Every equation, every observation, every theory represents the cosmos learning about itself through conscious observers. When Einstein discovered that space and time are woven together, that was the universe realizing something profound about its own structure. When Hubble found that galaxies are receding and space is expanding, that was the cosmos discovering its own dynamic nature. When particle physicists probe the quantum realm, they're helping the universe explore its own fundamental constituents. Yet, for all we've learned, mystery persists at every scale. We've discovered dark matter and dark energy, while having no idea what they actually are. We've found that consciousness emerges from neural activity while remaining baffled about how subjective experience arises from objective processes. We've traced cosmic evolution back to the first fraction of a second while being unable to explain why anything exists at all. These mysteries aren't failures of science. They're invitations to continue the cosmic journey of self-discovery. The universe's mysteries ensure that future generations will have their own adventures in understanding. Children born today will grow up to ask questions we haven't thought of, make discoveries that will reshape our cosmic perspective, and feel their own sense of wonder at revelations yet to come. The universe is still young, still evolving, still surprising itself with new forms of complexity and consciousness. We are part of an ongoing story whose future chapters remain unwritten. As you drift toward sleep tonight, carry with you the profound recognition that you are both infinitesimally small and infinitely significant. You are made of atoms forged in stellar cores, arranged in patterns complex enough to contemplate the very stars that created you. You are the universe's way of experiencing beauty, seeking truth, feeling love, and finding meaning in the vast cosmic dance of matter and energy. In your dreams tonight, you might journey to distant galaxies, witness the birth of stars, or explore dimensions beyond our perception. These dreams, too, are part of the cosmic story, the universe imagining new possibilities, exploring alternative realities, or simply resting after another day of conscious self-reflection. Sleep well, fellow traveler, through space and time. Tomorrow brings new opportunities to marvel at this extraordinary cosmos we call home, to ask new questions about its nature, and to participate in the ongoing adventure of consciousness exploring itself. The universe is vast, mysterious, and beautiful beyond comprehension, and you are both its child and its witness, both its creation and its way of knowing itself. Sweet dreams, and remember, wherever you are in this infinite cosmos, you are exactly where the universe needs you to be, to understand itself a little better. In you, the cosmos has achieved something magnificent, the ability to look back at its own history with wonder, forward to its own future with hope, and inward to its own complexity with awe.